In our talk about lenses and mirrors, when they form images, we were using an idealized system, especially with lenses. Mirrors, we had the simple law of reflection, and that works with mirrors. But when we talked about lenses, we assumed what's called the thin lens approximation, that the focal length of the lens is much, 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 much larger than the thickness of the lens itself. But in reality, that's not always true. Since real lenses don't behave exactly like a thin lens, you can get some optical distortions in the image. We call these distortions aberrations, and we have different names for them depending on the type of distortion. So chromatic aberration is actually a color information. If you recall, because of dispersion, different wavelengths of light bend differently in glass because they have different indices of refraction. Blue light bends more than red light. So if you create a lens and have white light showing through it, the blue focal point is slightly different than the red focal point for a real lens. This will cause problems in photography if to focus on an object you had to choose to focus on the red light and have everything have a blue glow around it, or focus on the blue light and have everything have a red glow around it. You can correct for chromatic aberration by adding additional lens elements. That's why camera lenses are as complex as they are, but it's still present, usually on a much, much smaller scale. It's not noticeable in the photographs we take, but it is still there. There's coma. Coma is just an aberration or distortion caused by an off-center object. We've assumed to this point that the object we're looking at is on the optical axis and then focuses an image on the optical axis. But the further you get from that optical axis, the more the lens can cause this distortion or coma, which basically makes, rather than having a focal point, you have a focal shape, it's sort of a teardrop shape coming out from the main focal point. So it can create blurring or distortion of the images. And then there's the general spherical aberration, which is just caused by rays that go through the lens having different focal points away from the lens based on how they come in. A very common spherical aberration is called astigmatism. Many of you, if you've had glasses or contacts, you might have astigmatism. It's the primary thing that's wrong with my vision. Astigmatism means that the lens is tipped slightly, so the focal length in the horizontal axis is different than the focal length in the vertical axis. You can correct that using lenses, contacts up to a point, or having the surgery done, of course, the laser surgery, to reduce or eliminate astigmatism, but it is an optical or spherical aberration, optical distortion, caused by a misshaped lens. And there's radial distortions. Now, radial distortions aren't really that obvious in, like this webcast. The bar above me, the curves above me, it looks fairly straight. But let me zoom out a second. So this is me completely zoomed out, going as far back as this webcam goes. Now this webcam is a short-range webcam. I'm not standing more than probably 4 feet from it. It has a very wide field of view, as you can see. But that wide field of view causes sort of a fisheye or a radial distortion, called a barrel distortion or a fisheye distortion, depending on the type. And you can see that the bar above me is no longer perfectly straight. It looks kind of bent. Or the piece below me looks like it curves up in the end. They are, I assure you, completely parallel, but the optical aspects of this lens system gives it this spherical aberration, which is one of the reasons I have it zoomed in to eliminate that, and also because you don't need to see the wall up here or the dry erase markers that I'm using in order to do this video. So there are a lot of different types of aberrations that we need to correct when creating a real lens system. So a telescope really isn't just simply two pieces of glass put together, or a mirror and a piece of glass. A microscope isn't really just two pieces of glass. You can create a very simple microscope using that, but modern complex microscopes and telescopes have a whole wide array of different types of lenses with different indices of refractions, different shapes, in order to minimize these distortions. You can never eliminate them. Chromatic aberration for a lens, there is no chromatic aberration for a mirror, but these systems, right, you can never eliminate, but you can minimize. You can reduce their effectiveness so they're barely noticeable using the system that you choose to use. A famous example of spherical aberration, most of you are probably too young to know this, but the famous Hubble Space Telescope, which in 2017, at the time of this recording, is still actually active in space, when it was first launched back in the 80s, right, early 90s, it actually had a spherical aberration problem. It actually was, the lenses or mirror was not crafted exactly to specs, and it passed, unfortunately, through the inspection process. And so when the telescope first took its pictures, I believe it was of Jupiter, they were fuzzy. And the Hubble Space Telescope cost over $1 billion to make, and it took bad pictures. And NASA rightly was raked over the coals by the public on this. It wasn't until the first service mission, several months later, up to maybe even a year later, where they put in additional optics. They basically gave Hubble glasses. In the optical path, they put corrective lenses, and Hubble then worked beautifully. But initially, it had a rather bad spherical aberration because of a misshaped mirror. So lens systems are actually quite complex, but we were looking at only at the simplest example using this thin lens approximation in our previous discussions.